Okay, so I thank the organizer for having the opportunity to be the last speaker of this workshop. It's the first time in my career that it happens, so it's a great honor. So I changed the title a little bit. Well, I can first remove my mask. And what I would like to address is the collectivity in connection with a shell structure far from stability. And I will deal essentially with some topics which have just been addressed in the previous talk. So I think it was a good planning of the from the organizers. So as an introduction, I just recall that for example, in the landscape of medium mass nuclei, there are some a range of phenomena which have been observed. Here, in red are emphasized the so-called location of. Okay, maybe I should. They don't see you. They don't see me. Maybe I should speak closer. Is it recording also? Okay. Can I move the? No, it's the mic. So. Yeah, this so-called location of the island of inversion. We have heard many talks, physics talks in the light system. I will rather deal about the island of inversion in a heavier system here. But in fact, what I would like in the before going to the results, trying to set a kind of general scheme in which we can understand the physics which is developing with simple picture. Of course, for each case, more dedicated studies and details can be derived. But I would like to set up a kind of general interpretation. It's not paged. I'm stuck. Okay. Is it? So yeah, so in the medium mass nuclei, as I already said, there are well-known vanishing of shell closure, but also occurrence of new shell gaps, island of inversion, and some specific low-lying excitation. And this variety of phenomena, what I would like to emphasize here is that is dictated by the shell structure, but this shell structure has a close connection with the collective behavior, so that in addition, for a given, I would say, collective behavior, this description can be achieved within a kind of shell model view as an interplay between the monopole field that I will and the multiple field that I will introduce more in detail in the following slides. The monopole field in the shell model language is, I would say, the spherical mean field. And the remaining part of the two-body Hamiltonian is the so-called multipole Hamiltonian, which drives the correlation. And as I like to quote this old quote from André Zucker, it's that usually the multiple correlation propose some solutions to the system, the pairing and the quadrupole, but it's of course the shell structure, the monopole Hamiltonian, which will decide which kind of feature will be developed. Okay, so I mean, if I would like to sketch a general framework, far from stability, what is occurring is that I mean, if I start to go from stability to a more exotic system, usually at the stability, the magic numbers are associated with energy gaps in the spherical mean field. So to promote particles above the Fermi levels, it costs energy. However, it's well known that some intruder configuration can overwhelm their loss of monopole energy and gain huge correlation energy. This is well known in stable magic nuclei like calcium 40 or even oxygen 16, where you have coexisting spherical deformed and super deformed states in somehow in a very narrow energy range. And at the very neutron rich or even proton edges, the different T equals 0, T equals 1 channels of the effective nuclear interaction, they will of course obviously weigh differently than they do at the stability line. So therefore, the effective single particle energies may suffer important changes, leading in some cases to vanishing of well-established shell closure or to appearance of new shell closures. Okay. So, for example, one can understand in simple geometrical physics the development of vanishing of shell closure in around n equal 8, n equal 20, n equal 40, and even around n equal 70, as the excitation of some neutron across some potential shell gaps and development of collectivity due to the quadrupole geometry which is lying at the Fermi surface. I will try to emphasize this mechanism in particular around the n equal 20 shell gap. So the theoretical framework that I will use is the shell model one. So I will just sketch the actual possibilities within the traditional shell model for those who are not so familiar with it. So in the shell model framework, you will define an effective interaction connected to a valence space. It means that you assume that you have an inert core, valence orbitals, which are supposed to carry the needed degree of freedom for the description of your phenomena of interest. And once you have defined your effective Hamiltonian, and also I should add here your effective operators, because the transition operator will also need some renormalization, you build and diagonalize the matrix. And with this efficient method, you are able to describe many phenomena at the same time. This can be collective excitation, weak processes, shell evolution far from stability in collection with astrophysics and nuclear synthesis. But you can add, we have seen in the present workshop, also if you get rid of the core, you can carry some ab initio calculation with the modern EFT realistic interaction. Just a word about the computational challenge for the shell model. Usually you have an exponential growth of the basis dimension because it will scale like the combinatory of your proton and neutron numbers into the valence orbitals. Actually, with standard shell model calculation, the largest dimension that you can face are of the order of 200 billion, either in the around nickel 78 or in the tin region with core excitations, and it carries a very large number of non-matrix, non-vanishing matrix elements. So the largest diagonalization with somehow relatively modest computational ratios are, for example, performed in Strasbourg with the two available M-skin and coupled skin code. In order to promote our field also is that I borrowed this picture from a particle physicist. Well, it's they are still referring to CD-ROMs at that time, so it's quite old, but I mean, you can catch the message. So during 1 year of LHC data collection, they were facing to data which could pile up into a 20-kilometer CD-ROM tower. I mean, if you refer to the number of information that you need when you diagonalize a shell model matrix, for one state, you can rise the 8 of the Mont Blanc. For one nucleus, several states, you are facing with the data quantity that were handled at that time at LHC during 1 year. And if you you compute during 1 year, you also handle a large amount of data, and this is of course something we should be proud of. So the largest matrices contain up to 10 to the power 14 or 15 non-zero matrix elements. It's obviously not possible to store them on hard disk, and you need to compute them on the fly. Well, you can decide to store it on hard disk, but I don't think it's the most efficient way to tackle the problem. As a teasing for alternative methods, we have just, if you would like to go beyond the actual diagonalization limit, to have your system, I just quote here rapidly. It's a little further away from the content of what I will address later. But for example, it was possible recently, this paper, which was published in May, with Duc Dao, who is my postdoc, is working in Strasbourg, to provide the first shell model calculation for super heavy nuclei. So we just developed a method which is using the mean field method. So you don't work within a spherical Slater determinant basis, but you rather expand your wave function into deformed Hartree-Fock basis. Here is the projected minimum for the case of nobelium 254, and with the use of rather well-known generator coordinate method, you can mix several states within this potential energy surface to end up, for example, with the very good description within a few basis states of the rotational band of nobelium 54, the location of the k equal 8- isomer, and even the multiplate 3+. So here the band rate is a little bit too low, but we had absolutely no parameter, and with a few kV monopole shift, we will work on that. It's possible to shift up a little bit this band. Now I will address the other obvious ingredient that you need for the shell model is the Hamiltonian. So nowadays the Cayley effective field theory interaction are extensively developed, and one can see some beauty, as was sometimes addressed within this in the complexity of these methods. But also the beauty, this is what I would like to extract here, it can be also traced back in the simplicity description of the nuclear Hamiltonian. So I try to figure out something which is more, looks simpler for the introduction of some view of the nuclear Hamiltonian, which was introduced by André Zucker for a while now. Is that any effective interaction can be split in two parts, a monopole part and a multipole part. So as I already said, the monopole part is the spherical Mill field. Means that it's responsible for the global saturation properties and for the evolution of the spherical single particle levels. And the multipole part is the correlator, the pairing, quadrupole, and octupole. What is important to have in mind is that the expectation value of the total Hamiltonian is only given by the monopole part for closed shell nuclei and closed shell nuclei plus or minus one particle, if you remain in this schematic view. What is important, in fact, is that the multipole Hamiltonian can be written in two representations, the particle-particle and the particle-hole representation. And if you diagonalize, you are left with a few leading terms, which are coherent and simple in terms of schematic operators. So you have a L equals 0 isovector and isoscalar pairing, Elliott's quadrupole, some sigma tau, and additional multipole of which can be described by R lambda, Y lambda. But more important is that these terms are rather universal. It means that all realistic interaction give similar value and they scale rather simply with the mass number. Here, so first, for the main leading term, of course, the pairing you all know is the multiple correlator which will act on a pair of light particle, and it is the regime which sets up for superfluid nucleus. Where a typical example is the tin isotopes, and for the quadruple regime, it's the leading term correlator for deformed nuclei in open shell nuclei. Yeah, I just now emphasize the universality. So here you have a set of different realistic interaction. You have old KB matrix elements, some modified realistic interaction USDE, but now you have also more modern interaction, couple cluster derived interaction with free body force, and you have in medium SRG interaction with many body perturbation theory with and without free body force. And what you see, for example, in the pairing channel, that essentially they all are rather similar, of course, to a few percent or tens of percent, either in this particle channel for the pairing, but if you look at the quadruple, so the quadruple content is extremely similar, let's say within 10% variation. What is not similar is the monopole content, and of course, if you make a calculation without without the free body force, the monopole content will be different and will drive the development. As I already emphasized, it's the monopole which will drive the solution of the systems. So this kind of universality, this is for the, I forgot maybe to mention, is for an SD shell matrix element. You can get the same kind of universality. I have in my laptop, I did not put in a table, also some chiral effective field theory derived matrix element for the PF shell. But here is a comparison between some old realistic potential, some more modern USD, no, sorry, this is for the SD shell. I wanted to emphasize here on the PF shell, sorry. KB3 and DPF FPD6 interaction, but also for the Goni force. It was in the past we managed to compute the two-body matrix element for the PF shell with the Goni force, and the pairing content as well as the quadruple content is again rather similar and universal. So in a sense that not only the strength, but also the overlap between these multipoles and the schematic ones is rather strong. So now I will go to some physics results. Going from stability to more exotic system in a playground which will be composed of two major shells, the PF shell and the SD shell, and with the effective interaction which was mentioned in the previous talk, with a recent update during the pandemic. 10 minutes? Non, ça fait 18 minutes moi que j'ai compté. Ouais. Non, j'ai lancé mon chrono, c'est pas possible. Il y a des discussions aussi. Ok. Si tu veux pas de discussion, c'est vrai. Non, mais 18, ça fait 28. Ouais, ok. Tu m'enlèves un quart d'heure. Okay, so here we go from calcium 40 to silicon 34 and up to oxygen 28. What is important here is that the effective single particle energies in oxygen 28 are completely at variance of the standard ones that you usually see in textbooks around calcium 40. So the SD shell orbit remain always below the PF shell, but the F7 and the P3 orbitals do get inverted towards oxygen 28. But also what can see is that the SDPF gap indeed gets reduced from 7 MeV to only 2 MeV. So in fact, it's the neutron-neutron interaction which provokes along the oxygen the reduction of this shell gap, and it's the proton-neutron monopole part which restore the gap at the stability. If you look more in detail at what happens between, for example, double magic silicon 34 and magnesium 32, and make a spin tensor decomposition, in fact, if you look at the reduction of the gap from the calculation, the reduction of the gap, well, the increase of the gap, let's say it this way, from magnesium 32 to silicon 34, the gap is increased by 1 MeV, and this increase of the gap is carried essentially by the central and the tensor part of the nuclear Hamiltonian. Now, why such there is such a paradigm and occurrence of island of inversion closer to more neutron-rich nuclei? If you consider the fixed fixed configuration in competition at n = 20, so the closed shell configuration, 0 particle 0 hole, and the 2 particle 2 hole, one can compute the correlation energies for such configuration, and you obviously see that the 2 particle 2 hole configuration gets much more correlation energy for open system than the closed shell ones. So as a result, this is the difference between 2 particle 2 hole and 0 particle 0 hole configuration without the deformation correlation. So this more or less reflects the increase of the shell gap from oxygen 28 to calcium 40. If you on top of that add the correlation, you end up with a narrow region where the 2 particle 2 hole correlation are the leading ones. So as a consequence, for example, in the case of magnesium 32, you have the development of 0 particle 0 hole, 2 particle 2 hole, and 4 particle 4 hole in a very somehow narrow range. Here I have set up relatively the various fixed configuration. So this is the super deformed configuration of magnesium 32, the 2 particle 2 hole, and the 0 particle 0 hole. We are rather close in energy, and I will keep this going from silicon 34 to which is double magic to magnesium 32. One of course very different spectrum. In magnesium 32, you have the occurrence of very low-lying 2+ states and also 0+ states. And in fact, the 0+ state, these 2 states are resultant of a mixing between the 3 possible competing configuration. Ground state of magnesium 32 is dominated by 2 particle 2 hole configuration, and the excited state is a peculiarity. Is a mixture of the 0 particle 0 hole configuration and the 4 particle 4 hole. It's rather funny since these two configuration cannot mix directly, but through the location of this neighboring 2 particle 2 hole, the resulting is a kind of intricate state which is mixed of 2 objects which in principle are not connected by the nuclear Hamiltonian. So since I am in a hurry, I will try to go to even further away. So if you leave the vicinity of magnesium 32 and you go in direction of oxygen 28, so what happens? So here are the effective single particle energy updated, as I said, 2 years ago, where now the P3 half is below the F7 half, but even the P1 half is really close. And in fact, this will have an impact So at the Fermi level, you will have direct possible excitation of 1- type, because of course the d3 half and the s1 half can both couple to the p3 half and the p1 half. And this can be seen, for example, in the neon isotopes. These are the 2+ and energies, and as was shown previously, the neon isotopes towards n = 20 are very low-lying 2+ states, so they are extremely deformed. But this deformation is connected, of course, to the narrowing of the gap here, and but will also the narrowing of the gap and the location of low-lying intruder orbitals will have an impact on the E1 strength, which can be observed. So here I have plotted the E1 response in first in the full 1 h bar omega space on top of the SD shell. So if you are at the stability neon 20, the E1 response is located very high in energy. But if you go, for example, in neon 26, you start to see a low-lying part, so-called pygmy part, which is driving down. This can be compared if you fold the shell model results by some width. This can be compared with what have been seen experimentally in the past. And the major contribution comes from the neutron S1 half core orbitals to P3 half and P1 half intruder orbitals. But still, this remains essentially as the one particle, one hole level. But if you go now further in the SDPF model space with higher core excitations, what is seen, in fact, is that the strength does not continue, even though the first 1- state goes down in energy. In neon 20 and 22, the strength remains, the pygmy strength remains rather high in the spectrum because of the extra binding energy of the 0+ due to quadrupole deformation. So this is reflected here. You see that the E1, the 1- states goes down, but the strength is maximally the largest for 26-28 neon from this calculation. So the low-lying strength moves up in the island of inversion. So I will go to the final part. How much time I have now? 5 minutes? I am at 27 minutes, so I will take 7 minutes. So for the masses, just to recall, because we've heard about, it's well known that the oxygen masses are rather a peculiar playground. And from the experimental point of view, you already see that if you would like to reproduce or to fit the binding energy with simply a quadratic term. So this is pure phenomenology. You plot the binding energy here. At that time, I did not have exact values, but I could update now the values. But you know that the drip line is as oxygen 24. If you fit by the quadratic term, you often get bound oxygen 28. And simply by adding a qubit term, it's really, I would say, easy or natural to get unbound oxygen 28. And this is what have been seen and calculated by the many groups. I borrowed this picture from Nadia Smirnova's presentation, and the importance of the free body force in the explanation of the unbound oxygen 26 and 28. I will finish by looking at the physics which is developing the fluorine isotopes. So as I said, and I put emphasis on the effective single particle energies from the shell model, this inversion of the P3 half and F7 half orbital has been seen already some time ago, for example, in the spectroscopic factors which were measured in neon 27, where the ground state was a d3 state, but the first excited state was a 3 minus state, and the f7 half, the 7 half minus states coming from the f7 half were sitting already 1 MeV above the states. More recently, here is the, so in the past, we did not implement such a strong constraint on the single particle energies towards oxygen 28, and this is the reproduction of the separation energy that we got at that time in fluorine isotopes compared to more stable phosphoric isotopes. That was the calculation we made in 2014 with Alfredo Poves. But more recently, incorporating the neon 27 data and also some new spectroscopic results on masses and spectroscopy, for example, in this PRL paper from Olivier and Aldrich Ravel in fluorine 28. The fluorine 28 is characterized by a negative parity states, which also shows that the intruder states are already present at n equal 19. And in addition, there was an extraction of 80% of L equal 1 content in the ground states. That is 4 minus arises from the P3 half orbital. So I just quote here regarding the oscillation of the separation energy towards stability in the fluorine. There was the prediction of Marek Prochaszak and collaborators of a kind of anti-odd even staggering effect due to continuum coupling in the energies, separation energies. And the point was that it was difficult for them at that time there was not much data, and it was difficult to define which strategy to have for the continuum coupling in terms of strength of the matrix element. So now here are the present situation with the calculation that we have for the fluorine isotopes, and it seems so the new data which are here are from no, this one is 30, so 2930. The new data are from the Neuland Samurai collaboration, and it's the PhD work of Julian Kalbuth. So it seems that just getting the separation energy of fluorine, I think it's a typo, 36, plus the inversion of the P3 half and F7 half shell simply matches this odd even staggering in the fluorine. In other words, there does not seem that first that the reduction of this odd even staggering does not seem to arise from the continuum coupling, and is fully reproduced by an interaction which is also reproducing the most stable nuclei. So I tried to, and of course you may think that I have it was pure luck, but if you look now at this odd even staggering also in magnesium isotopes, the reproduction is extremely good. And I will finish trying to understand, for example, the core excitation effects, but so the reduction of this odd even staggering seems to be already here, at least at the zero particle zero hole level. Even if it's here, it's weaker. But so if you go from 0 particle 0 hole to 6 particle 6 hole, you have an increase here of the staggering, which matches the experiment, but still no need for continuum coupling. I tried to extract the pairing content for the phosphorus and the fluorine. You still have an oscillation of the T equal 1 pairing content. What is important here is that I looked at the wave function of oxygen 28, and the ground state is dominated by 97% of seniority 0 components. It means that all the particles are paired to 0. There is somehow a 50% closed shell component, but the rest are scattering of pairs from the SD shell to the PF shell. And of course, this pair scattering was mentioned by Vitex, and is also exposed in the Kevin Fawcett paper. But also in fluorine, the ground state is dominated by 70% of seniority zero components and more than 60% of SDPF pair scattering. So the idea is that, in fact, here are the variation of the intruder occupancies in the phosphorus and the fluorine. So in the phosphorus, you don't have vanishing of shell closure, so you fill the FD shell here, and then beyond n equal 20, you start to fill first the F7 half shell and the P3 half. What is occurring in fluorine is that you start to fill the PF shell already at around between 18 and 19, and you first fill the P3 half shell. And this is probably the difference in the pairing strength between the F7 half and the P3 half shell, which is also responsible for the erosion of this odd-even staggering. So I jump to my conclusion, just to say that the monopole drift develops in many regions, but the interplay between correlation and spherical mean field determines the physics. The line of inversion appears to be due to correlation, and even at the drip line, the bound state approximation seems to hold, and there is a strong superfluid regime with pair scattering from SD shell to PF shell, which has been seen, and this staggering does not seem to be originate to continuum coupling. So thank you for your attention.